Hello and welcome to this video. I am Karnesh Jory and this video is about getting started with programming in C++. In this video, we'll look at types, variables, constants, arithmetic and relational operators, arrays and pointers, and the user-defined types, that is, structures, unions, classes, and enumerations. We'll also look at namespaces and error handling in C++ programs. And finally, we'll have a complete example on queue management where a queue is implemented using a linked list. So let's get started on this introductory tutorial on C++ programming. The first program is Hello World. And the Hello World program in C++ is like this. The first line is a comment, and then we have the hash include for IOStream, which is the system header file for input and output operations. Now the line std:\cout less than hello world. The two less than signs is the put to operator, which means take the string hello world and put to std:\cout. std:\cout indicates the standard library and cout is the output stream of the standard library. So what we are saying is that take the string hello world and put to the cout stream of standard library. That's how hello world is printed on the standard output. Now we have the file helloworld.cpp and we need to compile it. We are having an Ubuntu Linux system and we will be using the G++ compiler for compiling it. We can check whether the G++ compiler is available using the command which G++. In case there is no output, it means G++ is not available and we can install it with the command sudo apt-get update and sudo apt-get install build essential. Now we have the G++ compiler. We can say G++ helloworld.cpp -o hello world, which builds the executable file hello world, and we can execute it with a command /hello world and it prints hello world. In the hello world program, it says std:\cout. Cout is a part of the standard library std. If you are going to use objects from the standard library multiple times in a program, you have to qualify the name with a std:\. You can avoid that by declaring using namespace std. After that, all objects in the standard library can be used without the qualification std:\. And we can remove the std:\. for cout. For compilation, we can type the complete command G++ again, or we can use a makefile. The makefile for building the target hello world is like this. It has a single target hello world. So if we have a makefile and the hello world.cpp in the current working directory, we can say make and hello world target is built. We can test hello world and it works fine. The basic entity in a program is an object. Computer programs deal with objects. A named object is a variable. Every object has an underlying type. A type defines how the object is represented in the memory and what operations can be done on it. There are basic types and then there are higher level user-defined types. Now we are looking at basic types. The basic types are char, bool, int and double. The char type is the most basic type in a computer. An object of char type stores a character. Bool is for Boolean type and it can store either a false or a true value. Int type objects store integers and double objects store double precision floating point numbers. The actual size of objects of these types varies from computer to computer. On x86-64 based computers, the size of char and bool is 1 byte, int is 4 bytes, and double is 8 bytes. Most of the time, the objects are named, that is, they are variables. Before a variable can be used in a program, it has to be declared. For example, here is a declaration, extern int x. Here, x is declared as an integer and the name x becomes available in the scope. A program is normally divided between multiple source files, and the extern keyword means that int x is a global variable in some other file. When we declare extern int x, we can use that variable x in the current file, and during linking, this extern int x is linked to the actual int x, which is a global variable defined in some other file. So this is an example of declaration of variable int x. When we say int x, x is defined as an integer. We are telling the compiler that there is an integer x, so it is also getting declared, but in addition to declaration, memory is getting allocated for x, and that memory for x stores the value of x. If x is a global variable, then it is initialized to 0 by default. If x is a local variable, it is not initialized, it contains a junk value. It is a good practice to initialize a variable explicitly, and we can say int y equal to 7, and y is defined and initialized to 7. Instead of assignment, we can use braces around the initialization value. For example, int z braces 17, z is defined and initialized to 17. Similarly, we can say double p braces 2.77, comma q braces 3.99, char c braces uppercase b, bool d braces true, and all these variables are defined and initialized. Auto. Instead of specifying the variable type, we can say auto variable name and initialization. The compiler figures out the type of variable from the initialization. For example, auto r equal to 271 semicolon, and compiler makes integer variable r with value 271. Auto can be used when the type of a variable is obvious. For example, the index in a for loop. Our next topic is arithmetic and relational operators. The arithmetic operators are for addition, subtraction, multiplication, and division. Then there is the modulus operator and unary plus and unary minus. For example, x plus y adds x and y, x minus y subtracts y from x, x star y multiplies x with y, and x slash y divides y into x, that is, x is the dividend and y is the divisor. The modulus operator is represented by the percentage sign. If x and y are integers, x modulo y, the remainder, where y is divided into x, that is, x is the dividend and y is the divisor, and x percent y gives the remainder. The unary minus operator. Minus y negates the value of y. If y was 100, minus y gives minus 100, and vice versa. Similar to unary minus, there is unary plus, but its use is rather limited in C++. It can be used to indicate a particular value is positive. It can be used for operator overloading in user-defined classes. It is there more for consistency and symmetry. Because there is unary minus, there is also unary plus. There are two special operators Increment and decrement. The increment operator adds 1 to the operand while the decrement operator subtracts 1 from the operand. Both increment and decrement operators can be used as either prefix or postfix to the operand. In case of prefix, first the increment or decrement operation is done and then the concerned variable is used in the expression. In case of postfix usage, first the variable is used in expression and then the increment or decrement operation is done. For example, plus plus I, add 1 to I prefix. I plus plus, add 1 to I postfix. In these cases, there is only one operand in the expression, so prefix and postfix have the same effect. But consider this, x equal to a plus plus I index. Increment index I first and then assign ai to x. And x equal to a index I plus plus postfix. First assign x equal to ai and then increment index I. The array index value are different in the two cases and a different array element is assigned to x in these two cases. Relational operators. The relational operators are less than, greater than, less than or equal to, greater than or equal to, and not equal to. For example, x is less than y, x is greater than y, x is less than or equal to y, x is greater than or equal to y, x plus y is equal to a plus b, and x is not equal to minus 1. Bitwise operators. There are 6 bitwise operators which can be applied to operands of types char, short, int, long, and long. The operators are ampersand for bitwise and, pipe for bitwise inclusive or, caret bitwise exclusive or, that is XOR, less than for left shift, greater than for right shift, tilde for unary one's complement, that is, if a bit is 1, it is set to 0 and vice versa. Here is an example of using bitwise operators. We have a variable unsigned short flag and we'll try to change some of the bits of this flag. We also define another variable unsigned short mask which will help us in modifying the bits of flag. What we will do is that we will first set the bits in the mask and use the mask to set the designated bits in the flag. The difference between the mask and the flag is that we do not care about the rest of the bits in mask. The remaining bits in mask can be 0 or 1 depending upon the operation. But we care about the remaining bits in the flag. These must not be modified. The remaining bits in flag must remain constant during the modification of the designated bits in flag. The first task is to set bits 0 and 4 to 1. Regardless of the contents of flag, bits 0 and 4 are to be set to 1. We should not disturb other bits, only bits 0 and 4 should be set to 1. Bit 0 is the least significant bit. We set mask to hexadecimal 11. That is, we set mask such that all bits other than 0 and 4 are set to 0 and bit 0 and bit 4 are set to 1 in the mask. Next, we do bitwise OR of flag and mask, storing the result in flag. Now bits 0 and 4 of flag are set to 1 after the bitwise OR operation. The next task is to set bits 2 and 3 and the process is similar. After that, we want to reset bits 1 and 2. That is, bits 1 and 2 should become 0. So we make mask as 1's complement of hexadecimal 6. After that, all bits of mask other than 1 and 2 are 1 and bits 1 and 2 are 0. Why do 1's complement and why not specify the mask simply as FFF9? because this solution is independent of the size of flag and mask. We do bitwise AND of flag and mask, and the bits 1 and 2 become 0, and the rest of bits of flag are the same as before. Now, very important, we want to check whether two of the bits are having certain values. Had the problem been checking just one bit, that's simple. For 2 bits, we define a mask with values for those 2 bits, and the rest of the bits are 0. Then we do a bitwise AND of flag and mask, and if the result is the same as the mask, then those bits 3 and 4 in this case are 1. So our answer is affirmative. To check our solution further, we set bit 4 as 0 and do the test again. This time the answer is negative. The basic assignment operator is the single equal to sign. Now suppose there is a statement like x is equal to x plus y plus z. If we write a statement like this, x is being evaluated twice. First on the right side of the equal to sign and then on the left side. We can avoid that by saying add y and z and add the result to x. That is x plus equal to y plus z. Plus equal to is another assignment operator. It is a single lexical token, so there should be no space between plus and the equal to sign. Similarly, there are other assignment operators for other binary, arithmetic and bitwise operators. So the full list of assignment operators is equal to, plus equal to, minus equal to, star equal to, slash equal to, modulo equal to, bitwise or equal to, bitwise and equal to, bitwise XOR equal to, left shift equal to, and right shift equal to. These operators are heavily used in C++. They are concise, convenient, and lead to more efficient code. And before we leave the topic of operators, let's take a quick look at the precedence and associativity table. When an expression contains multiple operators, which operations are done first? The precedence table has multiple rows and each row has one or more operators. Each row defines a precedence level and the rows in the table are in the order of decreasing precedence. The operation involving higher precedence operator is done before the one involving a lower precedence operator. The table has rows with multiple operators. What if an expression has 2 or more operators of the same precedence? In that case, associativity comes into picture and the operators are grouped left to right or vice versa depending upon the associativity. So if the expression has x slash y star z, slash and star are at the same precedence, but the associativity of these operators is left to right. So first x slash y is calculated and then the result is multiplied by z. And here is an example program with 2 expressions, answer 1 and answer 2. What do they print? The variables I is 7, j is 1, k is 3, l is 2 and m is 12. First we print l, which is 2. Then we look at the expression answer. The increment operator has the highest precedence, so l becomes 3. Now the expression is 7 plus 1 slash 3 into 3 plus 12. Slash and star have higher precedence than plus. So first 1 slash 3 star 3 is computed. Now slash and star have the same precedence, so associativity comes into play and slash and star associate left to right. So 1 slash 3 is computed first. Since the variables are integer variables, 1 slash 3 becomes 0. So 1 slash 3 star 3 is 0. So we are left with 7 plus 12, which is 19, and the answer is 19. Now let's go forward. L had become 3 after increment and we restore L back to 2. Now answer 2. First increment, so L becomes 3. Then the expression j star 3 slash k is 1 star 3 slash 3. The operators star and slash associate left to right. So first multiplication is done 1 star 3 becomes 3 and 3 slash 3 is 1. So we have got 7 plus 1 plus 12 is equal to 20 and answer 1 is 20. Normally we use parentheses to clarify the order of evaluation so that the programmer and the compiler are on the same page. Constants. Our next topic is constants. There are two types of constants in C++. The first is constant variables. These are evaluated at runtime. The second type is constant expressions, which are evaluated at compile time. Let us first look at constant variables. And this is an example program. So first we have constant int day hours equal to 24, which says day hours is a constant. Next, double r equal to 2.303. So r is not a constant. Next, constant double q equal to r. Q is a constant which is initialized from r and q is evaluated at runtime. Next, constant int temp. Now this is an error. A constant variable must be initialized at the time of definition and then you can't modify it. To emphasize on the fact that constant variables are evaluated at runtime, we take input into an integer p. Let's say the value input is 19 and we define constant int s, initialize it to p, then we print s, which prints 19. Furthermore, we define int t and initialize it to p slash r, t prints 8. Next we assign s, which was earlier defined as a constant. We try to modify s by saying s is equal to t. Now this is an error as s is a constant and cannot be modified. These errors are compile time errors. They need to be removed for the program to be compiled and run. Next, we have constant expressions. These are specified with the keyword constexpr. The definition of constant expression is that these are evaluated at compile time. It should be possible to evaluate a constant expression at compile time. Let's look at an example program. Cube is a constant expression function giving the cube of its argument, but square is just a function giving the square of its input parameter. Now let's look at the main. We have constant expression double p equal to 2.3, constant double q equal to 2.4 and double r equal to 2.303. Next statement is constant expression double s equal to p. No problem. P is a constant expression. It is evaluated at compile time. So s can also be evaluated at compile time and s is a constant expression. Next statement, constant expression double t equal to 1.55 into cube q. This is an error because q is not a constant expression. Q is a constant that is evaluated at runtime and not compile time. The same is true for next statement, constant expression w equal to 1.55 into cube r, because r is just a variable double r and not a constant expression. And constant expression double v equal to square p is an error because square does not return a constant expression. It returns just a double. But next statement, double w equal to cube p, although cube is a constant expression function, it can be used in non-constant expression context. Any constant expression function can be used in non-constant expression context, but not vice versa. We can remove these errors. Let's make q a constant expression instead of just constant, and r also constant expression. And let's make square as a function returning constant expression. Now everything should work fine. We can compile and run the program. It works fine. The next topic is arrays and pointers. An array is a sequence of objects of a base type occupying consecutive memory locations. The objects of an array are called elements of an array, and number of elements in the array, that is the array size, is prefixed at compile time. For example, int v10. V is an array of 10 integers. The square brackets is a declaration operator. It means array of. The index of an element in the array starts with 0. So int v10 array has elements v0, v1, v9. The index of the last element is 1 less than the array size. Pointers. A pointer variable contains the address of a base type. It is set to point to an object of the base type. We can define a pointer variable as int star ptr. Ptr is a pointer to an integer object. Star is a declaration operator. It means pointer to. The unary ampersand operator gives the address of a variable. For example, we can say ptr is equal to ampersand v5. Now ptr has got address of array element v5 and it points to the element v5. As ptr points to v5, we can access v5 as star ptr. Reference. Ampersand is also used as a declaration operator, as in the case int I is equal to 77, int ampersand j equal to I. Here ampersand gives a reference to the variable I. J becomes another name for I. The rules of reference are that a reference must be initialized at the time of definition. We cannot say just int ampersand j. It has to be int ampersand j equal to some integer variable. Second, once a reference has been created, it cannot be changed. That is, once I say int ampersand j equal to I, now j is fixed to I. It cannot be made as a reference to some other variable. Here is another example. Next is a function for getting the next integer. It is passed num as a reference to an integer, and that reference is a constant. If we try to change num, it is an error because num is a constant. So we make it an integer function and return num plus 1. Our next topic is loops. Loops are used to execute a block of statements repeatedly while a certain condition is true. We have while loop, do while loop, and for loops in C++. The while loop is the most fundamental. It is like while expression statement. The statement can be a single statement or a block of statements enclosed in braces. For each iteration, the expression is evaluated. If the expression evaluates as true, the statement block is executed. So if the expression is false, initially, the statement is not executed at all. The do while is a variation of the while loop. In while loop, the expression is checked at the beginning of iteration, while in the do while loop, the expression is checked at the end of iteration. That is, do statement block while expression. So at least one iteration is always done. Then we have the for loop, which is the most heavily used loop construct in programming. And the for loop is like for expression 1, expression 2, expression 3 statement. At the start of loop, expression 1 is evaluated. At start of each iteration, expression 2 is evaluated. If expression 2 evaluates as true, the statement block is executed. Otherwise, the loop terminates. At the end of iteration, expression 3 is evaluated and the iterations continue. In the for loop, any or all of the 3 expressions can be omitted, but there must be 2 semicolons in the parenthesis after the for keyword. Here is an example of for loop for printing and adding elements of an array. Here, V is an array comprising of double precision floating point numbers, and we use the loop for printing the elements and finding the sum of all the elements. It works fine, and we have a variation of for loop called range for statement, which was officially added to C++ in C++11 standard released in 2011. It is for type element range expression statement. The range expression is a sequence like an array or a vector or simply comma separated values and closed in braces. For each iteration of the loop, the next element of the range expression is copied in element and the statement block is executed. Let's look at the previous example, substituting the old for loop with the range for statement. Then the for loop becomes for auto x colon v and the statement block. For each iteration, the next element of v is copied in x. We can compile and it works fine. If instead of copy, you want to use the reference to the elements of v, you can say auto $x colon v. That is, add the ampersand symbol after the type and the reference to each element of v is used, and this also works fine. We have seen basic types like char, bool, int, double. Using these, we can define entities like price, quantity, name, age, etc. in our programs. But we need to define high-level entities like employee, equipment, customer, weather, geographical regions, etc. C++ provides extensive mechanisms for defining user-defined types. These are classes, structures, unions, and enumerations. And we start with classes, which is a central concept in C++ and in object-oriented programming. A class is a type. It is a user-defined type, just like their basic types like char, bool, int, and double. We have user-defined types, and one of them is class. And just like we have variables for basic types, there are objects for classes. What do the objects comprise of? An object has members, data members or attributes, and code in the form of methods, which are actually functions. So broadly speaking, an object contains data attributes and methods. Or we can say an object encapsulates data and methods. Encapsulation means data and methods are put together as in a capsule. It leads to information hiding. The methods tell about interface to the class, how the users can use the object of the class. But the implementation of the class is well hidden from the users. The users can focus on the usage of the class without worrying about the implementation of the class. For example, here is the class Q. As you can see, it has members in the form of functions, that is methods, and data. Now there are public methods which can be accessed by any part of the program, and there is a private member. Private member can only be accessed from within the class, or it can be queried or updated via a method. So for the class Q, there is a constructor for creating an object of the class Q, and the constructor ensures that the Q object is created and initialized so that it's ready for use via the interface methods. We have another method, push, for adding to the tail of the queue, and then the method pop removes the element at the head of the queue. Then there are 4 methods which are constant methods. They do not modify the object, they only for query purpose. Peek head tells about the element at the head of the queue. Peek tail tells about the element at the tail. IsEmpty tells whether the queue is empty or it has some elements, and printQ prints the queue on the standard output. We'll have a full program about implementation of the class and its usage a little later in this video. The next user-defined type is structures. We have seen classes in previous slides. Let's look at this program. It's a very simple program, a class with 2 data members, and we define an object myTry, and we try to modify the member I for the object myTry. This gives a compilation error. We have not specified whether our members in the class try are public or private, and we are trying to update a member. By default, all members of a class are private. So in this class, try, int I and double j are private by default, and when we try to modify a member I for object myTry, we get the compilation error I is private within this context. We can solve this problem by declaring I as public in the class try. What is to be noted that by default all members of a class are private. Struct is the same as class except that by default all members of a struct are public. So if we change class to struct, this program should compile and it does. So between classes and struct, both are the same except by default all members of a class are private, whereas by default all members of a struct are public. Another example of a struct is struct employee. It is a constructor for creating an object of type struct employee. And skipping the next few lines, we see there are 3 private members, 3 strings, empid, name and address, all about employee. And in our program, employee E1 is created with the empid ABC123, name John Dow, and the address is DEF456. And that is using the constructor. The constructor has the same name as the structure and it has 3 parameters in parentheses followed by member initializer list, which tells empid takes the value of S, name takes the value of T, and address takes the value of argument U. And the object is created with these values. And even though the member name is private, we can access it using the method getName and modify it using setName. So cout less than E1.getName prints the value of employee E1 and we can modify it using the method setName. We can compile and run the program and it works fine. The next user-defined type is unions. A union is a struct that holds only one of its data members at any time. So the memory is allocated to a union is at least equal to the size of the largest member of the union. I say at least because the compiler might add some padding for alignment of variables. But the key point is that there is only one data member stored at any time. All data members are stored at the same location and there is space for the biggest data member in the union. For example, in the struct employee, we may wish to add the date of birth of the employee, but for some employees, the exact date of birth is not available, and for that we add approx age. So either date of birth or approx age is added to the struct. We can define union DOB or age, string DOB, int approx age. We can add this union to the struct employee and we need to keep track whether date of birth or approximate age is available for any employee. So we keep a flag DOB available, which if true means DOB for the employee is available, and if it is false it means that approx age is available. Enumerations. Next we have enumerations, user-defined type, which is abbreviated as enum. And we have 2 types of enums. First the plain enum and second the enum class. The plain enum defines a type whose variable can take a set of values. For example, we define 2 enums as primary colors red, green, blue, art colors purple, gray, yellow. A variable of type primary colors can take a value red, green or blue. For example, primary colors P equal to red. P can take a value of primary colors only. Suppose we say P equal to art color purple, this is an error. Or if we say P equal to 6, this is also an error. But plain enums are not perfect. We can say if P equal to 0 and this is okay. Or if P equal to art colors purple, this compiles with a warning. But there is a more significant problem. Once you say primary colors red, green, blue, red, green and blue are constants in the scope of definition and cannot be used in definitions of other enums. For example, art color purple, gray, yellow, red. This gives an error because red is already part of the primary colors. The solution is to use the second type of enum class. Let's look at it. An enum class provides a set of values, but the values are available only in the scope of the class. For example, we can have enum class primary colors red, green, blue, and enum class art colors red, yellow, green. The red of primary colors is different from the red of art colors. So we cannot say primary colors p color equal to red. This is an error because red is not available in the global scope. It is only available in the scope of primary colors, and a different red is available in the scope of art colors. So we should say primary colors p color equal to primary colors red. This is okay. Also, primary colors p color equal to art color red. This is an error because p color is an object of the class primary colors. The default operators for enum class are assignment, initialization, and comparison. We can use static cast to convert an object of enum class to an int. So, int I equal to p color. This is an error, but what we can do is int I equal to static cast int p color. This is okay. Real programs are big and developed by many teams, often separately. Also, we use libraries, the standard library, and third-party libraries. So it is necessary to have a mechanism that global names in libraries and software components do not clash. Namespaces provide that functionality. All declarations that belong together are put in a namespace, and when we use a name like a class name or a function name, we qualify that name with a namespace. For example, std:" cout. Std namespace is most commonly used. Suppose you want to use a different implementation of some class or function, we can define a namespace and put that class or function in that namespace. For example, here we have a different implementation of strcpy, and we define strcpy in namespace mycode, and we use it like mycode : strcpy instead of std strcpy. A program can have errors. These can be syntax errors or logical errors. Syntax errors are like misspelled names, missing terminators like semicolon, unbalanced parentheses, etc. These are detected by the compiler and need to be corrected before a program can be compiled. Then there are logical errors like segmentation fault, divide by zero, memory allocation errors, etc. And these are not recoverable. They have to be corrected before a program can run and produce results. A program can have exceptions, and the executable statements of a program are contained in functions, so we can say a function can have exceptions. Exceptions are like certain event like invalid parameter, index out of range, a logically not meaningful situation like asking for an element from a queue when the queue is empty. The main thing is that program can handle an exception, recover from it, and continue working. So while coding a function, we identify the exception, and when an exception occurs, the function throws that exception. It does so using the throw statement. The calling function knows that the called function can throw particular exceptions. So it puts the function call in a try block. The try block has catch blocks which catch the exception and execute exception handler. If the exception is not caught, the program terminates. Here is an example of throw, try, catch blocks. The function f1 throws two exceptions, runtime error and invalid argument. The main function catches the runtime error and prints the message. Then there is catch ... which is for catch all, that is, all exceptions that have not been caught so far in previous catch blocks for this try block. We can compile and run this program and it works as expected. And now an example program which is an implementation of a queue using a linked list. What is a queue? A queue is something we see so often in our daily lives. Queue is when people get in a line with an objective. Everybody gets into a queue at its end or tail and slowly progress towards the head of the queue. After getting to the head of the queue, the relevant event happens. The objective of getting into the queue is fulfilled and the person leaves the queue. A queue is a first in, first out data structure. If X gets into the queue before P, X will get out of the queue before P. In the example program, we represent a queue with a linked list. A person is represented by a structure named element which contains a person's name and a pointer to the next element in the linked list. Comparing the linked list representation with the real queue, the pointer next in the struct element points to the element behind, and the next pointer in the last element, which is the tail, does not point anywhere. It is the null pointer. Elements are added to the queue at the tail. The only way an element leaves the queue is that its objective of being in the queue is fulfilled. For example, a person gets the movie ticket, and that happens only for the element at the head of the queue. In our representation, there are two pointers, head and tail, pointing to the head and tail of the queue, respectively. The next pointer of the last element is the null pointer. It does not point anywhere. It is kind of wasted. We can make it point to the head of the queue and do away with the head pointer. So the head of the queue is pointed by tail pointer next. The code for the example program is organized in three files. First, there is queue.h, which contains the declarations of the queue. Any program that wants to use our queue has to include queue.h. Then there is queue.cpp, which contains the class implementation of the queue. And then there is user program userqueue.cpp, which uses the queue, and the source files. This is queue.h, which contains the declaration for the class queue. The queue class has public methods, the constructor for creating objects of class queue, and the destructor for deleting objects of the class, the method push for adding elements to the queue, and pop for deleting element from the queue. Then there are constant methods. These do not modify the object of the class queue, but are only for printing information about the queue. Then we have private data members, which can only be accessed from the class and not by user programs. There is declaration for the struct element and pointer tail, which points to the tail of the queue. We do not keep a variable for the head because tail pointer next is the head. Next, we have the file queue.cpp, which implements the queue class, and we have the constructor which initializes the queue. It makes the tail as null pointer. Initially, there are no elements in the queue, so the tail is null pointer. Next, we have the destructor for the queue. We want to delete the entire queue and release all the dynamic memory, sort of clean up. Here, we scan the entire queue starting from the head and delete each element one by one. After the destructor finishes, all elements are deleted and the value of tail is null pointer. Next, we have the push method where we add element and adjust the tail pointer. Then there is the method pop to delete the element at the head of the queue. The element is deleted and the tail pointer is adjusted, and the name of the element deleted is returned to the caller. The method peek head tells about the element at the head of the queue, and peek tail tells about the element at the tail of the queue. There is a method isEmpty which tells quickly whether the queue is empty or not, and we have the printQ method which scans the queue from head to the tail and prints the names in the elements. And we have the user program userqueue.cpp to try the methods of our class queue. We define the class command for the commands to execute the various methods of the queue. In the main program, we define lowercase q as an object of class q, and we have a menu to give commands. For each menu option, we take input if there are input parameters to be taken and call the public methods of the class q. It's in a loop, so it goes on till you choose the quit command. And this is the makefile for building the program. We can compile and build the user queue programs, and we can run it. It works fine. We have taken an overview of C++ programming in this video. We have also seen an example queue class. You can find all this information at SoftPreog website. Here is the QR code and the link is there in the description. Please subscribe to SoftPreog, click on the bell icon and enable notifications. Thanks very much for watching. Take care and stay safe.